Welcome back. Today I will be discussing Cowan chapters 8 through 10, namely automobiles and automobility, taxpayers, generals, and electronic communication and social control. And okay, so let's move ahead. Cowan chapter 8, automobiles and automobility, the auto cycle. In the middle of the 19th century, inventors realized that a self-propelled vehicle would be an adequate substitute for a horse and buggy. Inventors soon realized that an internal combustion engine would be required. In an internal combustion engine, fuel is burned directly in the cylinders to power them, as compared to an external combustion engine, such as a steam engine, where there is an external chamber where the fuel is burned. The first step in this direction was taken by a German inventor named Nicholas Otto when he invented the Otto cycle in 1876. This cycle involves 4 stages. The first cycle, the intake cycle, the intake valves open and the piston moves downward to force in the fuel. The second cycle, the compression cycle, the intake valves close and the cylinder moves upward to compress the air-fuel mixture. The third cycle, which is the ignition cycle, the compressed air/fuel mixture is ignited, which starts the cylinder on a downward movement, which supplies the power to ultimately move the automobile. And finally, the fourth cycle, which is the exhaust cycle, the exhaust valves open and the piston moves upward to exhaust the burned gases from the cylinder chamber. Who invented the automobile? There is some discussion in Cowan regarding who invented the first automobile. The person most commonly credited with inventing the first automobile is Carl Benz in 1885/1886. I had the good fortune of visiting Mercedes-Benz in Stuttgart, Germany, just after they had acquired Chrysler. During this visit, while I was in the Mercedes Museum on company grounds, representatives of Mercedes started the original Benz car for the Chrysler executives. The single-cylinder, 3-wheel vehicle made a large racket, smoked, and vibrated tremendously. There's a picture of it on the view graph here. Okay, the beginnings of the automobile. Steam-powered automobiles. The initial work on automobiles involved steam-powered cars. The steam-powered car was faster than any gasoline-powered car, and in 1906, a Stanley steamer broke the land speed record traveling at 127 miles per hour. That seems incredibly fast for 1906. Unlike the gasoline-powered car, they didn't need cranking to start the engine, which was a very dangerous proposition. The fuel, however, was quite heavy and bulky, and they needed a warm-up period before they could be started to get the steam to be generated. Okay, the electric-powered automobiles. Electric-powered automobiles also didn't need hand cranking, but their range was limited and the top speed was only about 20 miles per hour. Their batteries were also quite heavy and they frequently needed replacement. With the invention of the electric starter by Charles Kettering, eliminating the need for hand cranking in 1912, the utility of the internal combustion engine and the utility of the electric internal combustion engine, both the electric car and steam-powered car companies eventually went out of business. The first American car was produced by bicycle mechanics Charles E. and J. Frank Dewey in 1893. Most of the early American automobile companies were assemblers rather than manufacturers. They bought motors and other parts from manufacturers and assembled them in garages, sheds, and warehouses. Okay, custom-made cars. By 1910, there were 2 ways to manufacture cars. One way was to hire carpenters, cabinet makers, and other skilled craftsmen to manufacture bodies, often partially made from wood. These were made to customer specifications, and then they were assembled one at a time on a chassis consisting of a frame, engine, suspension, and drivetrain. These custom vehicles were for the well-heeled, and they were a statement of affluence and position. The second way was mass production, which we will discuss in the next section. Ironically, the most opulent and luxurious automobiles were built during the Great Depression. Custom coach builders such as Ralston, Murphy, and Fleetwood designed what I consider the most beautiful automobiles ever built. This is a Duesenberg you see on the slide. I took this in the Auburn Cord Duesenberg Museum. During this period of extreme poverty, names such as Duesenberg, Cadillac, LaSalle, Packard, Pierce Arrow, Lincoln, and others manufactured stunningly beautiful cars for movie stars and dignitaries with 12 and even, as in the case of Cadillac, 16-cylinder engines. Eventually, the Great Depression caught up with even them, forcing a great contraction in the number of car companies and the demise of the custom car builders. Henry Ford and the mass-produced automobile. Henry Ford Motor Company in the late 19th century produced a little more than just race cars. Hard to believe that Ford only produced race cars. In 1902, Ford financial backers, frustrated by his insistence on producing only racing cars, decided to close the company. This always amazed me, how the different turns of events led to other things. They called in Henry Leland as a consultant to appraise the plant and its equipment so that they could sell it and get out of the business. Just so happened that Leland had developed an engine under contract to Oldsmobile that produced 23% more horsepower than the standard Oldsmobile engine, but Olds rejected it. He showed the engine to the financial backers and convinced them to stay in the automobile business. Thus, he started the Cadillac Motor Company. So Cadillac grew out of Ford, kind of amazing. Henry Ford, of course, continued in the automobile business, and in 1903 formed the Ford Motor Company. He developed the first mass-produced car called the Model N, which he brought out in 1906. This was followed by the more famous Model T in 1908. Ford could not keep up with demand for the Model T, and as a result, a modern assembly plant in Highland Park, Michigan was opened. This plant incorporated overhead conveyor belts to move heavy parts and specialized assembly tools. Between 1912 and 1914, Ford engineers installed continuous conveyor belts, thus creating the world's first assembly line. Assembly line production enabled Ford to replace skilled workers with unskilled workers who had a specific task to perform in the assembly process. Remember when we were talking about muskets and Eli Whitney and that sort of thing? Well, this is the outgrowth of that. The assembly line dramatically increased Ford's profit margin, and this is the important thing, allowed him to drastically cut the price of the Model T. Other companies were forced to install assembly lines or to compete, or they'd have to go out of business. The significance of all of this is that Ford had produced an automobile priced low enough that the average consumer could buy it. Okay, Alfred P. Sloan and the mass-marketed automobile. Henry Leland, we're continuing now with this amazing chain of events. Henry Leland sold Cadillac to William Durant of General Motors in 1910. Durant formed General Motors in 1908, hoping to make it a company manufacturer of cars and automotive components. In 1916, Durant purchased Buick and Chevrolet, so he had Cadillac, Buick, and Chevrolet, as well as car parts manufacturers Delco and Hyatt Roller Bearing Company, which at the time was owned and managed by Alfred P. Sloan. Now, he plays a major role in a minute. You can see how all these things kind of fold into one another to make history. In 1918, Durant purchased Fisher Body Company, and he formed General Motors Acceptance Corporation and acquired Frigidaire. 1 year later, having overextended his company's capabilities, he was relieved of his duties, and a few years later, Alfred P. Sloan, became head of the massive company that Durant had created. When Sloan took over General Motors, the company was hopelessly disorganized with all these different companies that he just bought willy-nilly. What Sloan did for the automotive industry, that is to create an organizational model that would be followed by most modern companies, was every bit as important as Henry Ford's creation of the assembly line. So let's look at his organization, which for some of you taking business will seem quite familiar. Sloan reorganized General Motors, whereas he was the president of the company, so he was the number one. Reporting to him were the vice presidents who headed up each division. That division, Chevrolet, Buick, Cadillac, etc., would operate autonomously except where overall policy decisions had to be made. Each division was a separate profit and loss center, so the performance of each division was easily monitored. Certain agencies such as research and development and advertising were centralized and acted in an advisory capacity to each division. So you see kind of the structure of the modern corporation which Sloan pioneered here. Sloan's organization was the exact opposite of the way that Henry Ford ran his company. Henry had complete authority over every little detail in his company. Henry Ford made only one car at a time, the Model T until 1927, and the Model A between 1928 and 1931. Ford's Model T was only offered in black. A famous saying of Henry Ford was, "The customer can have any color he wants as long as it's black." General Motors had a variety of cars from Chevrolet to Cadillac in a variety of colors to satisfy the budgets and tastes of a variety of consumers. In addition, the third thing that Sloan had that was different than Ford, he introduced the annual model change, where the current year's model could be differentiated from the previous year's designs, whereas the Model Ts and the Model As during their production run differed very little from the version produced in previous or subsequent years. So he kept those cars the same, whereas Sloan introduced model changes, which we're now familiar with. Okay. There have been many recent developments in the automobile industry. Among these are the electric car, such as the Nissan Leaf, Tesla Model S, Model X, and Model 3, Chevy Bolt, and others. The self-driving car, ride-sharing services such as Uber, Lyft, etc. All these promise to revolutionize not only the car designs as we know them, but the basic way we use cars. I will leave you to read the balance of the chapter, but I would like to comment on a few points made by Cohen. On page 206, Cohen comments about the 60s being a time when bigger engines and more horsepower was better. The second car that I bought just after I graduated college was a 1967 Chevrolet Corvette Coupe. It had a big block 427 cubic inch or 7-liter engine with 435 horsepower. It got between 11 and 14 miles per gallon, depending on my driving style. Usually I got the 11. You really didn't care because in those days, Sunoco 260 or Super Shell which were the only two gasolines this car would run on, both ultra-premium gas blends only cost 24 cents per gallon. At the bottom of page 215, there is talk of a gas rationing during the Arab oil embargo. Excuse me. I remember in New York, depending on your license plate number, you would queue up on odd or even days, depending on what your plate number was. People were even shot dead, believe it or not, this is true, for cutting the queue at the pump. It just wiped out. On page 219, Cohen mentions a joint venture between General Motors and Toyota in California, and then moves on, but I happen to know a little bit of background behind this joint venture. This was a joint venture whereas the same vehicle, the Chevy Prism, the Chevy was called the Prism, Toyota was called the Corolla. The same vehicle was produced with only taillights, grills, and a few other incidental changes. This plant in Fremont, California, ironically, is now the home of Tesla Automotive. It's funny how things change. Okay, let's move on to the next chapter. Okay, Cohen, Chapter 9, Taxpayers, Generals, and Aerospace. The early days of aircraft and the aircraft industry. Samuel Pierpont Langley had the distinction of having been awarded the first U.S. government contract for aircraft development. Langley had been experimenting with internal combustion engines attached to gliders for many years, but the expense of building prototype vehicles was becoming too great to be borne by his salary alone. Theodore Roosevelt wrangled $50,000, a very large sum in those days, to support the experiments. On two separate occasions, in the autumn of 1903, the plane that Langley built with the money was catapulted off a houseboat in the Potomac River. Both attempts were failures, and the plane had to be fished out of the river. 9 days later, as they say, the Wright brothers flew into history. The Wrights hesitated to publicize their achievements until their patents were secure, but they had a rough idea of how they were eventually going to turn a profit. "It is our intention," Orville announced, "to furnish machines for the military first before entering the commercial field." Their fledgling company delivered its first airplane in 1909 to the War Department of the United States for $28,000, a sum that covered not just the plane itself, but also a year's worth of development testing. By 1911, almost a dozen American firms had begun manufacturing aircraft, but none were very profitable. Most of the planes they produced were purchased either by wealthy men or the military. The Army and Navy intended to use them only for surveillance. Built out of wood, these early planes were called biplanes because of their double wing structure, and they also had open cockpits and only one engine. None were large enough to carry freight or more than one passenger. Okay, World War I. World War I changed everything. By 1914, the British, the French, and Germans entered the war with small numbers of aircraft that they intended to be used, again, remember, just for reconnaissance. By the time the United States became a combatant 2.5 years later, air battles had become commonplace. Aircraft production had accelerated, and machine guns had been adapted to aerial warfare. So you had the dogfight going on. World War I was the first air war and also the first total war, the war in which governments learned how to mobilize civilian enterprises such as aircraft manufacturers on a massive scale. The war in which, for the first time, civilians far from the front lines were endangered by attack from the air. During World War I, the government used its power as a very large customer to aid in the development of both the aircraft industry, to aid in the development of the aircraft industry. The birth of the aircraft industry had made the total war possible. The advent of the total war made the growth and development of that industry both an offensive and defensive necessity. Okay, after the war, after World War I, most knowledgeable people in the military services had come to believe that the aircraft industry had to be kept healthy in order to provide for the nation's defense. How the government was going to participate in doing this during peacetime, with peacetime budgets, was resolved during the 1920s in two different ways. The first way was for the government to build an airmail service. By 1930, the Post Office Department's airmail business was used not only to support the aircraft manufacturers, but also the newly created commercial, to support not only the manufacturers, but also the newly created commercial airlines. The fledgling airlines struggled to survive, but in 1925, in order to alleviate their plight, Congress passed legislation requiring that the Postal Service contract its airmail service with commercial airlines. This legislation, the Kelly Act, salvaged many of the struggling passenger airlines. The Kelly Act also encouraged aircraft manufacturers to modify the World War I designs so as to be able to carry greater weight and provide both freight and passenger compartments. So they became larger so they could carry freight and also passengers. With assured government contracts for airmail, there was no doubt that the airlines could become long-term, large-scale customers of aircraft, thus keeping the aircraft manufacturers in business during peacetime. The second mode of government support is in research and development. In 1915, a rider was attached to a naval appropriations bill that provided for the creation of the National Advisory Committee for Aeronautics to supervise and direct the scientific study of the problems of flight with the view to their practical solution. During World War I, the NACA, as they were called, answered queries for the armed services and ran experiments at naval laboratories. It also laid plans for the construction of its own laboratory to assist in airframe and engine design. World War II, a turning point. World War II was the first war in which military strategists assumed that supremacy in the air was going to be a key, some said the key, component of victory. Yet in 1939, when the war began in Europe, the United States was not prepared to fight and win in the air. In 1939, the American Air Corps had 26,000 personnel. The British Royal Air Force had 100,000. The German Luftwaffe, 500,000. The President of the Congress began to increase appropriations for the purchase of military aircraft, and those appropriations kept increasing over the next 6 years. Shortly after the United States declared war in 1941, new plants were built and later new production techniques were introduced. In 1939, the entire United States Air Corps, had only 800 modern planes. The British had twice that number, and the Germans 8 times that number. Remember, 800 airplanes when we entered the war. At the war's end, the entire American aircraft industry was capable of turning out 110,000 aircraft per year. So we started out with 800. By the end of the war, 110,000 aircraft a year we were capable of turning out. World War II was thus the first war in which the nation's scientists and engineers were almost completely mobilized for the war effort. Many people believe that the techniques that were developed during the war for managing large-scale research and development projects were the most revolutionary techniques of all because they had such a profound impact on the post-war years when the hot war turned into the Cold War. Okay, World War II production at Grumman Aerospace. That's the company I worked for. To put this in perspective, Grumman Aircraft at its peak produced 664 aircraft in 1 month during World War II, a production record that has never been equaled. 2 out of every 3 Japanese aircraft shot down during World War II were shot down by Grumman aircraft. The mural shown depicts the typical production of aircraft during the height of World War II. It was meant to convey a sense of history to the current employees of the company, as well as a pride of workmanship. I spent many moments studying this mural, and each time I looked at it, I would see something I hadn't noticed before. The gentleman, by the way, painted on the door in the middle of the mural is Leroy Grumman, founder of Grumman Corporation. Okay, so let's move on. The military-industrial academic complex. The Cold War began even before the Hot War had completely ended. Throughout World War II, the alliance that was fighting the Axis had been a rather tenuous affair. Its weakest link, the relationship between the United States and the Soviet Union. At the same time that President Truman and his advisors were worrying about how to end the war against Japan in Asia, they were also starting to worry about how to counter the Soviet threat in Europe, and how the expansionist intentions of the Soviet Union were going to be contained. 4 years later, in 1949, these worries became even more pressing when the Soviet Union tested its first atomic bomb, making it clear that there were now 2 superpowers in the world, each potentially in a technological position to destroy the other, perhaps even destroy the Earth. With the outbreak of the Korean War in 1950, Congress began allocating more money for research and development, $3.1 billion in 1953 alone. Some of this was allocated for new research and development facilities owned and operated by the government. Yet another portion of it, $350 million in 1949 to 50, spilled over into research and research laboratories owned and operated by private industry. Another substantial amount of federal research funds went into universities. Thus, under various guises, American universities were becoming the government's partner in the arms race. By 1959, when President Eisenhower warned the Congress and the country about the dominance of what he called the military-industrial complex, the federal government, in the name of military security, was calling a very large number of tunes. So many, in fact, that some industries and universities became almost entirely dependent on the federal oligarchs. By 1964, 3/5 of all scientists and engineers in the United States, whether employed in industry, academia, or government service, were financed in some way by the federal government, 3/5. A close relationship had always existed between the federal government and manufacturers who supplied it with armaments. In the years after World War II, that close relationship was extended to many more industries as well as to universities. When there were 13 major U.S. aircraft manufacturers, certain aircraft companies were favored by certain branches of the service. These manufacturers were, by design, scattered geographically around the country, such that in the event of a bombing attack or a missile attack, only a portion of the nation's military production capacity would be affected. Grumman, McDonnell, and Vought, which is also known as Convair, always fought it out for naval aircraft programs. Lockheed, Boeing, Douglas, Republic, North American, Martin, Northrop, and General Dynamics fought it out for Air Force aircraft contracts. Bell and Sikorsky always fought it out for Army contracts. Naval contractors like Grumman always built a number of different aircraft models, but at limited quantities. Thus, when one model was retired, there was always a number of others within the company to build. Typically during these times, an Air Force or Army house would experience a dramatic boom or bust cycle, with engineers becoming like nomads, traveling to where the jobs were. They built large numbers, but of only a single model aircraft. At the end of the Cold War, the government decided to dramatically shrink the number of aircraft manufacturers from 13 to 3 in a matter of a few years. We'll discuss more about that later. Okay, the space race. The political impetus behind the race into space was the American government's desire to demonstrate that the United States was scientifically and technically superior to the Soviet Union. Prior to the creation of NASA, the U.S. space exploration program was in the hands of various services in the military. The Navy had the Vanguard launch vehicle, and the Army had the Jupiter rocket. Competition between the services for the U.S. government money in lobbying as to who would be the first to launch a satellite caused considerable delays and lack of focus in the U.S. space program. All of this changed on October 4th, 1957, when the Soviets successfully launched the first man-made satellite, named Sputnik 1, to orbit the Earth. I can remember how stunned the American community was, as this was the first time in quite some time that we were second in technology development. Immediately, there was a greater emphasis in high school on science and math, and students were encouraged to pursue science and engineering as a career. There was also wild speculation as to how the Soviets would apply this new technology, including coupling it with a laser to create an orbiting death ray. The times were posted as to when the Sputnik would pass over, and people would gather to watch it pass. And I remember all it did was go beep, beep, beep. You could see it, and then it would just do this beeping thing if you had some way of picking that up. This put tremendous pressure on the services to successfully launch their vehicles, causing shortcuts to be taken in the preparation. The Navy was initially designated as the service to launch the first U.S. satellite. After several unsuccessful attempts by the Navy, the Army launched the first U.S. satellite, Explorer 1, on January 31st, 1958. Fully aware of the delays caused by military politicking, President Eisenhower proposed to Congress, on Wernher von Braun's urging, that a new agency be created, a civilian agency devoted entirely to space exploration. On July 29, 1958, the National Aeronautics and Space Administration, or NASA as we know them today, was created. A few weeks after Yuri Gagarin's successful flight, he was the first Russian cosmonaut or astronaut, President Kennedy announced that before the decade was over, the U.S. would put man on the moon. A large number of companies competed for various parts of this program, named the Apollo program. During the Kennedy administration, North American, later named Rockwell, was selected to build the Command Service Module, and Grumman Aerospace Corporation was selected to build the Lunar Module. When I first started on the Lunar Module program at 22 years of age, my first engineering job, I worked on the interstage pyrotechnic nut and bolt combination, making detail and installation drawings. I was eventually put in charge of the thrust translational controllers, or TTCA, and also the rotational controllers, the attitude controllers, ACA, that the astronauts used to maneuver and land the lunar module on the moon. Soon after the first successful moon landing on July 20th, 1969, the attitude of the public suddenly changed. On the missions that followed, the public went from a groundswell of national pride to an attitude of, what are we spending all this money going to the moon for a bunch of useless rocks? The aerospace industry into a lull for a time until Ronald Reagan was elected president. He devised a plan to bankrupt the Soviet Union by dramatically increasing the defense budget, increasing the number of aircraft built, and investing in programs such as Star Wars, the Star Wars missile defense system, and stealth fighters and bombers. The program worked, and on December 31st, 1991, the Soviet Union was officially dissolved. The three remaining aircraft companies after consolidation. For us in the aerospace industry, it was a bittersweet victory, as we could see the handwriting on the wall. Soon the government forced the consolidation of the aforementioned 13 aerospace companies into what is today 3 major aerospace companies capable of building military aircraft. They are Northrop Grumman, Boeing, and Lockheed Martin. No longer is there much competition for aircraft programs, which means higher pricing for aircraft. Of greater concern is our ability to respond to a major conflict, as we did in World War II, with our industrial base but a shadow of its former self, and much of our manufacturing and technical base going offshore. Okay, so let's move on to our final chapter, Cowan Chapter 10, Electronic Communication and Social Control. Communication is a fundamental activity in which all human beings engage. Electronic devices, radio, telephone, and television have had a profound and quite conspicuous impact on American society in the 21st century because they have altered patterns of communication, the way in which people convey information to one another. Like all profound social changes, the communication revolution has raised numerous troubling questions. Some of those troubling questions concern the issue of social control. Okay, so the first thing we want to talk about is wireless telegraphy. The history of modern communication technology begins not in the United States, but in the United Kingdom, Germany, and Italy. A 19th century Scottish physicist, James Clerk Maxwell, demonstrated that light was an electromagnetic wave, and he predicted on theoretical grounds that similar waves of different frequencies, either higher or lower than light, could be generated by electric discharges. In 1887, a German physicist, Heinrich Hertz, created an apparatus to generate and measure both high-frequency and low-frequency waves from a device called a spark gap transmitter. A few years later, Guglielmo Marconi succeeded in sending signals in Morse code, long sparks and short sparks, as far as 2 miles. He also developed a simple apparatus that would receive the waves, an antenna, and convert them into direct current, so that like telegraph signals, they could be heard by someone listening to the pattern of current through earphones. Marconi was not the only person experimenting with wireless telegraphy at the time, but he was the person who figured out a way to make money with it. Within 5 years, Marconi had become a very rich man, and wireless telegraphy had become a turn-of-the-century popular fad. Okay, let's move on. Wireless telephony. Wireless telephony was invented and commercialized by Europeans, but wireless telephony was pioneered by Americans. Among thousands of young men and women who became wireless operators were a few who realized that the next technically interesting and commercially exploitable frontier would be the transmission not of Morse code, but of real sounds, voices, and music, not just dashes, dots and dashes. In 1901, Reginald Feddersen designed a new kind of receiver, a heterodyne receiver, which could convert high-frequency waves produced by the spark gap transmitters into low-frequency waves, the kind that make diaphragms resonate in telephones. Excuse me. Feddersen took out a patent and went into business for himself and several investigators as the National Electric Company. In 1902, he designed a high-speed spark transmitter called an alternator that would transmit sparks so fast that the waves it created were almost continuous. Using equipment that would otherwise be sending Morse code, Feddersen succeeded in sending the first radio messages. Feddersen continued to experiment with voice transmission, and much of his energy in the next several years was devoted to perfecting his alternator and selling it to organizations that wanted telegraphy services. He also was embroiled in a patent dispute with Lee DeForest. Sometime in 1901, Lee DeForest made a patent application for a detecting device he called a responder, with his invention and a small amount of capital contributed by friends. He attempted to go into business, just as Feddersen had done, in competition with Marconi. DeForest caught the attention of a stock promoter by the name of Abraham White. Before long, White had created a new company, DeForest Wireless Telegraphy, and he brought it public with a 1 million stock offering. By 1904, the organization had leaped to 15 million, reflecting both White's public relations skills and the popularity of wireless telephony. In short order, however, Feddersen sued DeForest for patent infringement. When the suit was settled in Feddersen's favor in 1906, White used it as a pretext to do something he probably wanted to do for a long time, and that is drive DeForest out of the company that bore his name. DeForest, then desperate to invent something on which he could subsequently begin building another wireless empire, invented and patented the Audion. By adding a third element to a diode, DeForest created a triode, which he called an Audion, to signify that it could detect a continuous electromagnetic wave, the kinds of wave that made wireless telephony possible. The Audion was, in short, the ancestor of all vacuum tube technology, on which a decade later, radio broadcasting would be based. Excuse me. In 1912, Edwin H. Armstrong discovered that if current coming off the plate of an Audion was fed back into the grid of the tube, creating what was later called feedback or regenerative circuits, sounds could even be further amplified, making it possible to dispense with earphones. He further discovered a few months later that regenerative circuit could transform vacuum tubes into transmitters of electromagnetic waves. In the fall of 1913, Armstrong applied for a patent on his regenerative amplifying circuit, and in the winter for its transmitting circuit. Because he failed to interest either AT&T or Marconi in his patents, Armstrong sold the rights to his regenerative circuit to Telefunken in Germany. During World War II, during World War I that followed shortly thereafter, it became clear to virtually everyone involved in the communication industry that after the war, wireless telephony based on vacuum tube technology was going to become both feasible and profitable. A mass market for radio receivers, simple and durable instruments that people could use in their homes, was likely to develop. But who would reap the profits from the potential market? For the duration of the war, none of these questions could be answered. Okay, so let's move on to wireless broadcasting or radio. In the last months of the war, Edwin Armstrong had invented a super heterodyne circuit, 8 vacuum tubes that, when suitably modified and wired together in precisely the right way, could function as a receiver, tuner, and amplifier all in one, namely a radio. The Westinghouse Corporation purchased the manufacturing rights to Armstrong's patent in 1920. Frank Conrad, who worked for Westinghouse in 1919 using vacuum tubes, built a transmitter over his garage, and in 1920, he began broadcasting concerts from his home over his garage. In September 30th, 1920, a Westinghouse executive, Harry Davis, asked Frank Conrad if he could build a transmitter at Westinghouse headquarters in time to broadcast the election results on November 2nd. Davis, upon hearing a previous department store advertisement, had an idea. If there was voice transmission that everyone had been interested in receiving, then a potential market for receivers that Westinghouse could manufacture under the Armstrong patents would not be just for amateur operators, but potentially every American. If it could conquer the mass market, Westinghouse star might just eclipse that of RCA. On November 2nd, Warren G. Harding's defeat of James N. Cox became the very first newsflash, and radio broadcasting was born with Westinghouse Corporation as its midwife. In the first halcyon years of radio, performers flocked to radio studios. For singers and pianists and opera stars and politicians, the free publicity was sufficient inducement. But after a singer was asked to fill up to 20 hours of airtime, he or she began to feel exploited. Further, radio station employees that gave the news or the weather or reported on the games wanted to be paid. Who was going to pay all these expenses? By early 1920, someone at AT&T came up with an idea which would develop into what we have become to understand as commercial broadcasting. Why not sell airtime? In August 1922, AT&T station WEAF broadcast its first income-producing program. A 10-minute message and the first radio commercial was born with AT&T as his midwife. First radio commercial. Excuse me. In January 1926, spurred by internal fighting by the RCA consortium over who would control the radio market and possible antitrust legislation appearing, the first media network, the National Broadcasting Company, or NBC, was born. A few years later, Congress, which had again been under considerable pressure to create some order on the airwaves, passed the Radio Act of 1927, reaffirming some of the principles of the Radio Act of 1912, specifying some of the powers of the Secretary of Commerce with regard to broadcasting, and creating a regulatory body, the Federal Radio Commission, FRC, later called the Federal Communications Commission, or the FCC, to enforce the law. Okay, let's move on to television. I can remember when I was very young, sitting in front of the huge speaker at the lower part of the console radio, when my parents had to listen to such programs as Beulah, Amos and Andy, Boston Blackie, and many other radio shows. These shows forced you to use your imagination as to what was happening, because again, this was radio. The radio stood about 4 feet high and had a number of multiple radio bands. Some were short-wave bands. And you could select a station by either turning a knob or selecting one of the push-button preset stations. Sometimes the radio would play big band tunes, Tommy Dorsey, Glenn Miller. And on Sunday, my father would entertain us by singing, and not very well, religious hymns on the radio before we went to church. When I was about 6 years old, I was invited along with my sister and several of the neighborhood kids to sit on the showroom floor of the appliance building next to our house and watch a new invention called TV after the store was closed for business. So the owner would close the store and then let the neighborhood kids, smart marketing on his part, sit on the floor, and guess what they would ask their parents for shortly thereafter. Okay, so to a 6-year-old, this was like magic, seeing what looked like a movie coming from this small box like the one shown on this slide. My favorite show was the Cisco Kid, a cowboy show, and my favorite character was Pancho, a Mexican sidekick of Cisco's. The owner of the store would come in and we would draw straws. The one who drew the largest straw would be entitled to a free ice cream at the local ice cream parlor, which he also owned. Okay, television. The entire history of electronic communication follows the patterns established in the early decades of the 20th century in the history of radio. There were many surprises for individuals and organizations that think they can remain in control of the business of communications. Just when an inventor, after years of painstaking work, would begin to count his royalties in the millions of dollars, along came an inventor with a new, slightly better device, stealing his thunder and his plans for future wealth. Or just when a company, after years of complex maneuvering, would exert almost complete control over the marketplace, along came another company with a new idea to compete for market share. By 1920, electrical experts in several countries were experimenting with various ways to translate images into electromagnetic signals that could be carried through wires or projected into the atmosphere. One of these was Ernest Alexanderson of General Electric, who experimented with a revolving disc punched with spiral patterns of small holes, through which a light beam was detected. He hoped that this device would be able to digitize images, turn them into a pattern of tiny dark and light spots, so that they could be transmitted into electrical signals by another device, called a photocell. Two other experimenters, Vladimir Zworykin of Westinghouse and Philo Farnsworth, began to experiment with cathode ray tubes. They believed that if the pattern of the cathode ray tube could be controlled, they could be made to correspond to a generated image. Then these tubes would work better than the mechanical scanners, such as Alexanderson's revolving disc, to translate photographs into electricity. Farnsworth and Zworykin turned out to be right. By the latter part of the 1920s, both Farnsworth and Zworykin had acquired patents, and Alexanderson was conducting daily broadcasts. The commercialization of television was delayed first by the Depression, then by World War II. But what ingenious men had suspected in the 1920s was clear by the 1950s. Television had supplanted radio as the national means of communication, just as radio had earlier supplanted newspapers, the telegraph, and wireless telegraphy. Television has extraordinary popular appeal and has spread rapidly throughout the country, encouraged by the general expansion of the American economy after World War II. 8,000 American households had television sets in 1946, 45.7 million by 1960, just 14 years later. Yet by 1970, broadcast television, which had reigned virtually supreme for the previous 2 decades, was being challenged by yet another new medium, potentially more flexible and more global: cable television. Once a sufficient number of customers had become regular subscribers, the cable television companies invested some of their own funds in producing some of their own local programs in their local studios. But most of the material that came over the cable in early years was produced by one of the television networks. By 1965, however, the first communication satellite was put into orbit. That changed both the technology and the potential of cable television. Federal regulations created in the era of radio and television network broadcasting at first stood in the way of cable programming, but a series of executive and judicial rulings that organizations other than ComSat and Intelsat could orbit satellites gradually lifted these restrictions. By 1990, the social control that network television and other advertisers had once exercised over the context of broadcast had thus ended. Well, a lot of material in this week's lecture. But that's it for this week. Hope you have a great week, and we'll talk to you soon.